Welcome everybody to my presentation. My name is Fabian Muhs from the Institute of Aircraft Design at the University of Stuttgart, and my talk today will about the numerical characterization of FOLDCORES under shear loading. So let's start with a short look what exactly a FOLDCORE is and how we use it. We start with a flat base material, apply the folding edges, and then fold up the core to its three-dimensional shape. Then we apply the top and the base face shield and get a sandwich component with a fold core inside, like we see here on the left side. Due to this manufacturing process by folding, we are able to generate a wide range of different cell types, like we see on the right. Very easy one, like the Mu or Ori, more complex one, like these or these, and also curved folds with curved crease lines, or such challenging one, hybrid configurations with straight and curved crease lines in it. And the problem I want to address today is the characterization under shear loading and the anisotropy of shear loading. So in literature, there's often only a shear characterization in 0 and 90 degrees, but what if we have a shear angle of 60, 40, 50 degree? We don't know. And also we don't know what is the best geometry for a specific load case. The first thing we need to do is to develop a new design language to describe the FOLDCORES. We do this with Bezier-spline elements, and we describe the major crease lines with these elements, like we see in here on the left. We are able to describe straight crease lines, curved crease lines, and so on. After this, we use the reflection method, like we see on the right side, starting with this described curve. Then we introduce the parameter h for the core height and the parameter L. And with these two parameters, we are able to define the extrusion vector seen in red. And now we can extrude these major crease lines up to the base top plane and reflect down to the base plane and get a three-dimensional core shape. And per definition of the reflection method, these structures are always flat foldable. In the second step, we need to set up the numerical model. We use an implicit nonlinear time integration method with an interactive abort criterion to reduce the simulation time. Furthermore, we apply a model size reduction, and therefore we assume that we have an ideal stiff bonding between the fold core and the face sheets, and therefore we are able to use only one row of these cells in the L direction to represent the mechanical behavior of the core. In W direction, we apply periodic boundary conditions here on the red edges and able to reduce the model or up to only one unit cell. So we can represent mechanical behavior under shear loading with only one unit cell, which reduces the DOFs of the model significantly and speed up the simulation enormously. To validate this new numerical method, we build some real cores out of PET and test these cores on a universal test machine under shear in 0 and 90 degrees. The results for the shear modulus and the maximum shear stress for 4 geometries can be seen here for 0 degree direction and here for 90 degree direction. And we can see that the real test data matches really good with the FEA data, and the presented method can be seen as validated. So what are the application of the new numerical process chain? On the left side, we see the characterization of a Mu or Ori cell. Therefore, a simulation in 1 degree shear loading steps were performed from 0 to 360 degrees. And in the plot, we can see in blue the shear modulus and in red the maximum shear stress. And we can now directly see in which directions or in which shear loading directions the performance is better and in which direction it is not so good. So we can see here that in transversal direction, the performance is better than in longitudinal direction. A second use case would be, or can be seen on the right side. We introduce the anisotropic ratio, which is built by the mechanical parameter in the first shear direction divided by the mechanical parameter in the second direction orthogonal to the first direction. Then we can plot these anisotropic ratio versus the shear angle of the first direction. And if we now would like to achieve a specific anisotropic ratio like 1.2, we can directly find these 2 points here and see for which shear angle of the first direction we can achieve this anisotropic ratio. The same could be done for isotropic behavior, which is represented by an anisotropic ratio of 1.0, seen here by the red dashed line. So what is the conclusion of this work? We show a new design language for FOLDCORES using quadratic Bezier-spline elements and the reflection method, which is able to describe a wide range of unit cell designs. After this, we show a new numerical method using an implicit time integration with an interactive abort criterion. Furthermore, we reduce the model size with the use of periodic boundary conditions. Then we validate the results of the numerical process chain with real test data using cores out of PET. Last, we show 2 use cases. The first one was the characterization of a Miura-Ori unit cell in 1-degree steps under shear loading. And the second one was the achievement of a specific anisotropic ratio for the shear modulus. So the numerical process chain showing you today give us a very helpful tool to characterize and design foldcores for specific engineering applications. And we get a base knowledge about the mechanical behavior under shear for different foldcores. Thank you for your attention, and if there are any questions, please feel free to ask them. Thank you very much.